Good afternoon, everyone. And first, I'd like to thank the organizers of Pravarthana for inviting me. It's always a pleasure to be back because this is where I started my career. Though every time I come, I see fewer and fewer of my colleagues. They make basically they remind me that I'm getting old. Many of them are retired and some of them have left the place. So nevertheless, I'm happy to be here. I should say I'm a little bit unsure what I was expected to speak, because the theme of the conference or the workshop doesn't fit in with what I do. But certainly, if you find some of what I say interesting and applicable, please let me know. I'll also know what I'm doing is useful in other areas, right? So with that, I'll just talk about what I've been doing over the last 10 years or so of my work. Essentially, multivariate data analysis techniques for what I call a system of systems which are described by linear mixing models. This is a very old problem. It starts with linear regression, and today there are a lot of techniques such as principal component analysis and a variety of spin-offs from that being used, but they are used left and right without looking at the fundamental, without verifying the assumptions under which they have been developed. So my focus has been what are the underlying principles that govern these techniques? Are they applicable at all to certain systems? Why do they work? So with that, with a limited set of systems, we have been able to make progress and throw some light, so which I'd like to share with you today. Okay, so just to motivate you, some of the application areas which we are looking at is the standard linear regression, multivariate linear regression. And in this in particular, as engineers, we are interested in model identification from data. So one of the ways is you can write a first principles model, we all know, but today with the plethora of data that's coming in, it's also possible to identify models from the data. In particular, if you are interested in identifying what we call linear models, then you would use regression or any other technique, related technique. So what I'm going to talk about is the techniques which are applicable to developing models from or extracting models from data, linear models in particular, and calibration models from which you develop. The second application I'm going to talk about is blind source separation. The last one I'm not going to talk about applications in biology which deal with some structural information also that's available. So only the first two I'll probably will be able to talk about today. So just to give you a motivating example, the particular problem I'm interested in is to deal with what I call water distribution networks or power networks where energy is conserved. So this is a simple example of a flow system where a single inlet flow splits into two flows. Okay, so these are governed by, if you are writing a first principle steady state model, it would be a linear equation that in a flow is balanced essentially, right? So this is what basically we said at steady state, that you would expect the inflow to be equal to the outflow, assuming there is no accumulation in the unit. And I could write it in what this particular equation can be written in this matrix form, which is basically saying the coefficients are 1, minus 1, and the variables are f1, f2, f3. So this particular coefficient matrix, I would call it A, which is called the constraint matrix, and these are the true values that should actually satisfy this. What we are given is a sample of measurements of x, okay, multiple samples that are taken at different time instant, different operating conditions, and the question that we want to ask is it possible to estimate the model A from data? Okay, of course, I mean, we will worry about other forms of this, but in particular, we are interested in extracting this model from data. You may ask why. It's so easy to write this first principles model. Why are we actually going through touching the nose the long way? But it turns out, just to give you examples, that we have been looking at even the IIT Madras distribution network as well as those from cities, and it turns out the drawing is never updated. You will find that you have partial knowledge, and some of the lines that have been laid, additional lines, they have no idea. In fact, there are bypass valves that are placed on the lines that are permanently closed, and these people don't know that the line is active or not. So there is a fundamental problem of even getting the network structure correctly delineated before you can do analysis on it. So you have partial information, may not be you don't know, it is not correct to say that we don't know the entire matrix A, but we might have partial information and we need to build up on it. But first we are going to look at the problem where we don't know anything about A. We just have data, and is it possible to extract the constraint matrix? Later on we can add in the other additional information that we may perhaps have. This is one problem that and to motivate you, I'm going to look at another problem which is drawn from a totally different field, and it's in speech processing, This is a famous cocktail party problem, where there are multiple speakers, speaker A and speaker B, and typically if you are in the party and the human ear is so good that if somebody talks about you, even somewhere far away, the moment you hear your name, immediately your ear perks up to actually find out what they are saying about you, behind your back, of course. So essentially we are able to somehow source separate, we are able to extract that particular signal that is of relevance to us from this mixed signal that we are receiving. So the question that's asked in the cocktail party is, we have these several sensors, microphones placed in the room, okay, typically more microphones than the number of speakers, or it could be equal, just equal as I have shown in the figure. Here there are 2 microphones and two speakers, and the question is, all we receive is a mixed or a linear combination of what's spoken. So we might, this person might be speaking a steady stream of syllables, vowels, whatever, and then depending on the distance, this microphone will be receiving some weighted fraction of that, and it will also be receiving a weighted fraction of what somebody else is speaking. So ultimately what is received here is a linear mixed or weighted combination of what is spoken in the room by the different speakers. Similarly, this microphone receives a different linear combination of mixed signals, and the problem is, can we deconvolute, can we take the mixed signals, nothing else, and can we figure out how many speakers are there, what they are speaking, and so on and so forth, can we actually demix. Okay. So that's what we call the blind source separation problem. This is usually posed in the speech processing area, but it has application in also chemometrics. I'll just show you one more example before we talk about the techniques used for solving these. Here what we have is basically a mixed absorbance spectra of a dilute solution. Beer-Lambert's law says that if you have a dilute solution of several components, then the individual absorbances of the pure components multiplied by the appropriate concentration in moles will be the mixture spectra. So the mixture spectra is nothing but a linear combination of pure component spectra. So if I give you different mixture spectra, from the mixture spectra, is it possible to identify the pure component spectra? Again, this has several applications in reaction monitoring. If I continuously monitor a reactor where the species concentrations are continuously changing with time, and I sample it and I just get absorbance spectra online, from this data is it possible to deconvolute, get the concentration measurements, and from there build a kinetic model and so on. So that's a very useful application. A second application is in diagnosis, in medical diagnosis. Today they are looking at non-invasive techniques. Is it possible to take a urine sample from people and just look for certain metabolites which has a certain signature and then detect colon cancer, for example, and so on. So there are several different applications where deconvolution is again a very important kind of problem. Okay. So this is done in again using MEG data, EEG data for detecting onset of let's say epilepsy and so on. So those are several places where this linear mixing model is actually assumed or typically valid, and we ask these questions. Okay. So I'll just go on to the first technique that is very commonly used in a wide variety of things, but not in the same way that I'm going to talk about. They are just used for denoising for a variety of applications, but they all stem from this, at least in my belief, they all stem from the fact that there is an underlying linear mixing model. If it's not there, these techniques certainly should not work. Why they work, I don't know. People use it, and it seems to do a good job, but we're trying to actually figure out. But we know for sure if there's a linear underlying mixing model, then using these techniques give you very precise information, and that's what I'm going to elucidate for the next half an hour or so. So I'm going to start with principal component analysis and how you can answer the first question: is it possible to extract the linear model just from data alone? Okay, and I'll show that it's possible, up to what extent and so on. Okay, so again revisit the example. Just to remind you, what we are trying to do is that we have a bunch of variables x for which we have data. Okay, so we have a bunch of measurements of this vector x. Vector x itself consists of several variables, in this case only 3, but it could be several hundreds or thousands of variables for which we have data, and they are related by some linear equations which I call the constraint matrix. Remember here there is only one, but it could be many in number. Okay, several different things, and we are trying to estimate this matrix A, which means we need to know how many constraints are there and the coefficients of this matrix A and so on. All of this have to be found from data. Okay. So, just to show you, this is very closely related to the regression problem. We are not stating anything differently. There is a slight difference. In this case, there is only one relation between 3 variables. So, you could choose one of the flow variables to be an independent variable and the remaining 2 to be dependent, and you can write it in this form. That is, you can choose, for example, 2 of the variables, 2 variables to be independent and 1 dependent, because there is one constraint, there is one dependent variable. The remaining you can choose as independent, and you could actually say, I want to find this regression matrix that ties F1 to F2 and F3. The other one is an identity matrix, so you are not interested in identifying this, but typically you are interested in identifying this, what we call the regression matrix. There you have to specify. When we do linear regression, you have to specify what are the independent variables a priori, and then you actually find the relationship between the dependent and independent. In the form that I expressed, you do not have to specify what is independent and dependent. It is an implicit form. This is an explicit form. What I am interested in is in the implicit form. Once we get the implicit form, we can ask from the form, we can actually also specify the set of potential independent variables that I can specify. Not all combinations are allowed, and you can actually pinpoint which combination is allowed and so on. So, the way we have posed this problem here, it is what I would call the implicit form, which ties up all the 3 variables. This regression matrix is nothing but the explicit form, which you typically try to do with in linear regression. Okay. Now, again, there are 2, and linear regression itself, if you start off, there is a whole, a lot of literature on this. Depending on the assumptions you make, there are several techniques. The standard one that most of us are typically introduced to in a classroom or in a course is what we call ordinary least squares regression. There you explicitly specify the independent variables, and you are interested in finding the regression matrix. You typically assume that the measurements of the independent variables are noise free. You never question that, although you have put in a sensor and you have measured this, you typically assume that the independent variables are perfect, and essentially all the error is in your dependent variable, and you do a least squares minimization, you will get some solution, analytical solution for this problem. It is possible. That is called ordinary least squares regression. There is an alternate viewpoint which says, do not what I call treat different variables differently. All of them are equal in the eyes of God, man, whatever. So, why should we say that the independent variables are measured without error? Let us assume all of them are measured with error, okay, and then try to estimate this. That is called the total least squares problem. So, here we are explicitly, when we write like this and we apply ordinary least squares, we assume they are error free. All the measurements of the independent variables are assumed to be without error. Whereas, in the total least squares problem, we assume all the variables are noisy. So, it is called the symmetric treatment of variables, and the problem becomes difficult. That is one of the reasons they may not be introducing. In fact, in the general multivariate problem, there is no analytical solution to this problem, and therefore, maybe they do not introduce in class. It is not easy to teach this maybe in the preliminary class. But in general, in engineering systems, you will find that all variables that we measure have errors, and therefore, maybe TLS is the appropriate technique to use, and we want to find this regression matrix or the implicit form that we wrote, the constraint matrix, when all variables are noisy. So, we want to solve the problem in the TLS framework, and the claim is principal component analysis is a method that solves the TLS problem. In fact, it was originally developed in 1901. It is very clear that it is a solution of the regression problem. Although today they are using it for different purposes, but the origin, if you go back and dig in, you will find that essentially it was posed. It is a technique for solving what I call the TLS problem, total least squares regression problem in the multivariate case. Okay. So, let me post this as a optimization problem. What are we actually saying? That we have got measurements of small n number of variables, capital N number of samples, and we want to estimate those values, but you do not want to estimate each one independently. You want to estimate it such that they satisfy some constraints, and I do not know what these constraints are. I want to estimate also the constraints, but if you post this problem with no additional restrictions on A, you will get, it is not a well posed problem. You need to say something about it. So, one of the conditions that is written is the rows of A should be orthonormal. Okay. So, orthonormality condition is placed on the rows of A, because otherwise you can't get a unique solution. Okay. So, in order to get a unique solution, you post this. What this essentially means is you are not looking for a constraint matrix, but you are looking for the row space. You are trying to identify a basis for the rows of A. That's at most, and this is an orthonormal basis. That's what you are basically asking for. If you can get an orthonormal basis for the row space of A, you are satisfied. Okay. So from data you need to get this. That's the main aim of this thing, and you can actually pose different problems. So from this, depending on the assumptions you make, you can actually get a variety of problems. The early one which I worked on for the 30, 40 years without realizing that PCA has got anything to do with it. At that time, we were interested in, given this matrix A from first principles and given X measurements and given some idea of the noise in the measurements by means of the standard deviation, only find a consistent estimate of X. Find X which is consistent with respect to given A. We call that reconciling the variables, reconciling the estimates, so that you can get better, more accurate estimates and you can use them in your optimization exercise. So this was the problem that was where A was given. Now PCA says, no, I don't need to give what you call, I don't need A, estimate A from data, simultaneously estimate this such that this is satisfied. Only thing is orthonormality is what you call imposed on the constraint matrix, and in this case sigma is assumed to be identical. So it doesn't say that different variables have different noise accuracies. It treats all measurements of all variables. It assumes it has the same accuracy. Under that condition, you can show that PCA actually gets this, solves this problem optimally. Okay. So the next question to naturally ask is, what if we are not given sigma? We don't know the accuracies of the variable. Is it possible to extract it from the same data? It turns out that it's possible, and that turns out to be a thing that we did over the last 2-3 years. We have found out a method which basically can find out A, can find out sigma, can find out X, such that this is satisfied. Under this, of course, it sacrifices this condition and puts another condition, but nevertheless it's very similar to this. So it is possible to even extract the accuracy of the sensors from the data. You could ask other kinds of questions. You should say, well, in the source separation, you are saying that there are some sources that have actually contributed to the mixtures. Can I identify the sources themselves? I don't want a basis. I want the sources. Basically, the basis is kind of, you want a particular form of the basis, you might say. Blind source separation is basically a technique that blind source separation is a technique that attempts to get this form, but instead of saying, putting an orthonormal condition, it says, look, get me a particular form of the basis which represents the sources. And the way it does this is by putting in additional conditions of what we call non-negativity constraints. When I come to that, I will talk about it. Okay, so there are different variants of this problem depending on what information you think you know a priori and what information do you want to extract from data. Okay. So let me go back to this thing, PCA. What we want to do is find this A and X hat which satisfies this and so on, right? Essentially you are asking, in other words, I give you a data which is element of the n-dimensional space, real space. What you want to do is decompose the space into two orthogonal subspaces, one representing the data, the true data vectors lie in that subspace, okay, because they are all linearly related. They can't have the degrees of freedom that you have. So it's actually supposed the true values lie in a lower dimensional subspace. Find that lower dimensional subspace in which the true data vectors lie. That we call Vx. And the orthogonal complement, which is basically the rows of A which are orthogonal to it, that forms the remaining. So you are trying to break this n-dimensional space into two orthogonal subspaces, one in which you believe the true data lies, the other in which the constraints, the constraint defines the row space of the constraints. Okay, so you want a basis for these two subspaces. That's what PCA is trying to find. And the way it does is, I'll give the procedure. The formal proof that it does is actually can be actually shown. So what we do is basically arrange the data in a n cross n matrix form. N is the number of small n is the number of variables, capital N is the number of samples. Then we look for the eigenvectors of this covariance matrix. So this is just nothing but the covariance matrix of X. Notice that I don't have an offset term. Basically we have simplified the problem by saying there is no offset, everything passes through the origin. So in the regression case, if you want to compare it with regression, and we compute the covariance matrix and then we find the eigenvectors of the covariance matrix, and we can show immediately that the transpose of the eigenvectors corresponding to the smallest m eigenvalues define the row space of A. Okay, so if you want a row space array, a basis for the row space array, take the eigenvectors corresponding to the small m eigenvalues. You can show this is formal, this solves the problem. It's not just, it's an arbitrary procedure. You can show that this is optimal. It solves the optimization problem. It is maximum likelihood and so on and so forth. You can actually show under some condition. Okay. So just to go back again, the way we do it is using what we call the singular value decomposition of this matrix X, which is split into two parts. S represents the singular values of X, or these are the square root of the eigenvalues of the covariance matrix X transpose. These are the eigenvectors of X transpose U, columns of U, and what you want to take is the last m eigenvectors, and the transpose of this is your estimate of A. So that is what we are saying. If you are interested in the data space, you look at the first n minus m largest eigenvectors corresponding to largest singular values. The first part corresponding to largest represents your data space, a basis for the data space. The last m, which corresponds to the smallest, represents the row space of A. So you get, so I'll show you by an example that you get this, so that it's very clear that this is not just something arbitrary. Okay. So there are a few issues to this. You need to actually say how many constraints. PCA does not talk about it very clearly. It says choose m smallest. What is small? It uses some heuristic to actually define what is small. Essentially, several different heuristics are given. Okay. One is you look at the percentage of variance explained in the data, whatever that means. I mean, from an engineering viewpoint, you can't say much about it. It talks about variability in the data, and then talks about, okay, what percentage variance is captured by the small m eigenvalues. So if you say my data below capture has 95% of the variance is in the data, then you choose as many eigenvalues as necessary to explain 95% of the data. In fact, the sum of the eigenvalues is the total variance. So you can look for a simple criteria, k eigenvalues you choose such that the sum of the k eigenvalues divided by the total variance is greater than 95. That is just a heuristic. It does not tell you how many constraints are there in the process. Okay. The other thing is to plot these eigenvalues, log of the eigenvalues with respect to index, and look for a sharp change in the eigenvalues. And then you say, well, that is the actual number of eigenvalues you need to retain. The rest are all constraints, basically due to noise. So that is one other way. Then there are other kinds of validation methods and so on that are proposed. All of this are heuristic, no theoretical basis. Okay. At best you can say, well, sometimes you might win, sometimes you might lose in this. Okay. Is there a theoretical thing? And it shows you can formally show there is a theoretical way of getting the number of constraints, and I will just show it through an example rather than trying to give the proof for this. So I have taken a simple example where we have 5 variables and 3 constraints. The constraints are f1 is equal to f2 plus f3, or f1 plus f2 is f3, f3 equals f4, f4 equals f5 minus f2. Okay. What we do is do a simple simulation to set up the data, essentially perturb f1 and f2. You use a fluctuation which is of this order of magnitude. That means I have taken normally distributed data with base value 10 and standard deviation 1 and 2, and you get a set of samples, 1000 samples, and then compute the remaining through the equations. So this gives the true values of the variables. They lie in a subspace, 2-dimensional subspace of the 5-dimensional space. Then add errors to it. The errors we add by actually adding noise which have different variances, one having standard deviation 0.1 and so on and so forth. And then we get the measured data out of this. Okay, the measured data will lie in a 5-dimensional space because the errors will corrupt it. Okay, the true data lies in a 2-dimensional subspace. So apply this, apply PCA, and look at the singular values of the data. You can see the last 3 are small, or you can say there is a sharp change after the second one. So you can say that there are the data lies in a 2-dimensional space. There are 3 constraints. That is what this indication. So PCA is able to show you reasonably well. Okay, although there is a theoretical thing, but it shows that look, there is a sharp change in eigenvalues, and these are all more or less equal. So let us take 3 constraints, and the estimated A, which is basically the transpose of the 3 eigenvectors corresponding to these 3 smallest eigenvalues is this. You look at these numbers, they do not make any sense, obviously, because it is a basis. It is not the true constraints. You can't infer anything. So there is a tendency to look at this and say something, I mean, PCA is doing something, okay, and it is not interpretable. It is not true. It is interpretable, and it should correspond to this, but it does not, because this is a linear combination of the original. okay. Because it is a basis, it is some linear combination. How do we know it is a linear combination? How do you, there are several ways of testing this, and there are several different ways of finding out whether your estimated A is equal to the true A or the A that you prefer to have. So this is something what we call PCA is a scaling and a rotation ambiguity. What you estimate is some linear combinations or rotation of the original A. A hat, estimated A is some m times A, where m is some arbitrary rotation matrix. We do not know what that rotation matrix is, it depends on your data completely, okay. And therefore you cannot compare A and A directly, estimated A and true A element by element. One way of comparing is by using what is called the subspace angle, okay. You basically look for, just like you compare two vectors by the angle between vectors, there is something called a subspace angle, which essentially represents, you draw vectors in each of these two subspaces, find out the angle between the two vectors you draw, find the maximum angle that you can ever find by drawing two vectors in these two subspaces. If both are same, the maximum will be 0 still. If they are different, the maximum angle will be actually non-zero. So from there you can find out whether these two subspaces are equivalent. It does not depend on the basis choice. So you can use actually subspace angle, or you can actually drop perpendiculars from your estimated A to your true A, because in this case it is a simulated example. You know the true constraint matrix, row space, so you can drop a perpendicular and find the shortest distance between your estimated vectors and your row space. If the estimated vector is in the same subspace, angle again the perpendicular distance will be 0. So deviation from 0 is an indication that there is a problem. A third way of comparing is by constructing what is called the regression form, the explicit form, for some choice of the independent variables, and then you can compare element by element. The regression form is unique. The implicit form is non-unique, but the regression form is unique, because any rotation will actually get cancelled in this when you convert it to regression form. So essentially what we are saying, the regression form, you choose the independent variable subset and rewrite these constraints in this form by writing the dependent variables in terms of the independent, and this is your regression matrix minus AD inverse A. This you can do with the original A, with the estimated A. Now you can compare element by element. So these are different ways by which you can verify what you have found is actually the true. It's a linear constraints of the process. They are physical constraints. They are meaningful, not meaningless. Okay, just to give you some idea what without scaling, if you apply to the data, the kind of alpha distance between the estimated vectors and the row subspace of A turns out to be this. This is just the sum of all three, absolute sum. This is the subspace angle. If you properly scale the data using the noise covariance matrix, then you can actually get a very, very good fit. That subspace angle tells you that. In fact, less than 0.1 is what we believe is a good measure that you have found a good estimate for the constraint matrix. So here basically we are saying that if you scale the data properly, if only you knew the noise properties or noise variances, you can scale your data using that and you will get a very good estimate. If you do auto scaling or any other scaling which does not have knowledge of this, you will end up getting slightly poor. This is a particular case where the SN, signal to noise ratio, was high. So PCA does a reasonably good job typically. Okay. If you want to compare the regression forms, these are the two ways of comparing, as I said, finding the perpendicular distances or finding the subspace angle. You could actually compare regression matrix. This is a case of a regression matrix where I have chosen F1 and F2 as the independent flows, F3 as the dependent, and written in terms of the independent flows F1, F2. And if you look at the original constraints, F3 should be related to F1 and F2 in this fashion, or F3, F4, F5 are related to F1 and F2 in this fashion, and in this fashion from the true matrix, the estimated thing comes very close. You can do an element by element comparison and see where you got it bang on target. So you actually found the constraint matrix. Although the original A is not interpretable if you just look at the numbers, but actually they are representing some form of the linear constraints of the process. So what we are saying is that you can get the conservation principles or the mass balance equations from data. It is not that you need to know this, although in this case of course you can say it's simple and can get it. Remember, in a typical distribution network there might be leakages in the thing that are not known. So from data, if you get, it will pinpoint. From first principles you won't get that. So those are the those are the advantages when you go from data to such thing. Okay. So I have done the same case for a very low signal to noise ratio. The way we generate a low signal to noise ratio is by perturbing this with point, let us say 1/10 of this, 0.1 and 0.2, reduce the fluctuations, then they will be comparable to the noise, and therefore the signal variation will not be, will be comparable to the noise variation, and then PCA will not do a good job. The reason is the noise have got different variances, and PCA assumes sigma is same for all variables, and therefore it will not do a good job, and that is shown by the large subspace angle that you get between the estimated A and the large alpha values that you get. So if you don't do scaling, you get even worse. If you do some auto scaling, you can get, but if you scale with the sigma of the noise, you will get the thing properly. The big problem is you don't know the noise variance, and so therefore the next question is whether is it possible to estimate the noise from data, and that's what we are going to basically show. So some of the problems that PCA has, it assumes that errors in different variables have identical variances. It's called the homoscedastic assumption. So under that it will do well, or if the signal to noise ratio is very high, it will do a reasonable job. Model identified using PCA depends on scaling, and different people have suggested different scaling, and you can't quantify what this effect of scaling is. Optimal scaling was an unknown thing, but we know for sure now that scaling with the noise variance is the correct thing to do. Okay. So all these heuristic criteria used for model order, we said that the number of constraints have to be selected by looking at the eigenvalues, by eyeballing it, looking at scree plots and so on. So clearly that's not a very what I call nice solution to the problem. So we are going to look at all these things and provide a solution, and this is by estimating the error covariance from data, and it's called iterative PCA. It uses PCA effectively in an iterative fashion by combining with something else. So we are going to use PCA iteratively with a procedure for estimating sigma. So some of the conditions have to be satisfied. You can't have error. In general, you can say at every sample for every variable the error is different, or error variance is different. But typically if you use the same sensor repeatedly, unless it's a long period of time, if you have taken over years, maybe the sensor characteristics have changed. But if it's a short period, let's say about a few months or a few days or a few weeks, you don't expect the sensor characteristics to change. So we can make a reasonable assumption that the sensor inaccuracy or does not change over samples. It may be different for different variables because you are using different sensors for different variables. So your standard deviation of the error will be different for different variables, but need not be different for different samples. So what we call this variation of sigma along one mode, not along both modes. So the first assumption that's made is that error variances can change along one mode, typically in the variable direction. The second thing we say that the errors in different variables are uncorrelated. Remember that one sensor and another sensor, the error in that is unlikely to be correlated. Possibility of correlation is if ambient temperature changes, and that's a common source, or the power source, if they are connected to the same power source and power fluctuations causes errors, then you can say that the errors are correlated. Typically, but diagonal variances or uncorrelated errors is as assumed. Only under those conditions you can estimate it from data. Furthermore, you cannot estimate all elements of sigma. There are some conditions. You can estimate only as many as the constraints allow, okay, because that's the information you are going to use in estimating, and I will show what those conditions are. So there is a limit on the number of elements. For diagonal sigma, you can typically estimate everything. For off diagonal sigma, you can only estimate a very small fraction. Okay. So the idea is basically use PCA on the original data, you get an initial estimate of A. Then starting with this, you obtain an estimate of sigma by maximizing a likelihood function of some residuals, which I will show what it is. Once you estimate at sigma, you can scale the data. We know that if you scale the data by the error variance, you will get the optimal solution. So we scale it, now you get a new estimate of A, plug it in, get a new estimate of A, and iterate between these two steps and until convergence. So convergence can be proved because this optimization technique has a certain, it falls under a certain category called the majorization technique, and fortunately this particular technique is actually can be proved to be convergent. Okay, so what basically we are solving as an optimization problem is estimating x such that it satisfies, estimating sigma, estimating A, but I am not interested in A, I am interested only in some basis of A. The basis condition that we put is not A transpose sigma, but A sigma A transpose is equal to sigma. And it's clear what we are doing. We are actually transforming the problem from a likelihood, from a what we call the scale domain to a typical least squares by doing pre-scaling with this square root of this. So this condition arises because it's least squares in a scale domain. Okay. So if you really look at it, the scale data, you will find that this is basically a orthonormality condition of the A constraint matrix in the scale with respect to the scaled variables. So to solve this optimization problem, as I said, assume sigma is known, convert this to a least squares problem by scaling, so get A through PCA, and once you have A, construct what we call the constraint residuals, which is nothing but A times X. Remember that if the true value satisfies these constraints, then this should be only a function of the error, A times error, because A times X should be equal to 0. But notice that this, because of your incorrect estimate, maybe it's not true, but once you have converged, this one should be only a function of the sigma of the error. From this you can get the covariance matrix of this residual, and you can back out this estimate sigma from the distribution of, or the maximum likelihood function of these constraint residuals. If you ignore this, this is essentially saying that I get the covariance matrix. The easy way to interpret this is I have the covariance matrix of this sample. Okay. From there can you get out sigma. This is in a lower dimension, this is in a higher dimension, therefore there is a condition. The condition basically being the number of elements of sigma, remember it's diagonal, should be less than m into m plus 1 by 2, where m is number of constraints. You can actually show this formally by showing that the uniqueness of the solution is guaranteed only then. Okay. So you will be able to estimate this as long as the number of elements of sigma is less than m times m into m plus 1 by 2, where m represents the number of constraints in the problem. You don't know the number of constraints, therefore you have to again kind of iterate on that. We will see what that condition means again. So but if you solve this thing, you get a new sigma, plow it back here, again scale it, get a new A, and redo this, I mean, until converges. So I just want to show you some results that you can get for this simple problem. Fortunately it satisfies the condition. There are 5 variables, 3 constraints, so 3 into 4 by 2, 6 variables, 6 estimates I can get, 6 sigmas I can get. Fortunately I want to estimate only 5, so it's possible. So identifiability, we call this the identifiability condition. In statistics it's well known again. Essentially this particular problem I have chosen satisfies this, and therefore you can estimate and apply this, and you can show that for the high SNR ratio, theta subspace angle, after you have done all this, extracted the A, extracted the sigma, everything, you end up getting a subspace angle of 0.03. I just want you to compare this with the subspace angle when you scale it with the known sigma e. It's almost close. That means from the data we are able to extract this error variance as quite accurately. That's why you are able to get almost match it with the known sigma case. So if you know the sigma, you will get a subspace angle of 0.028. With the unknown sigma, you are still estimated sigma, you are still able to come close. You can compare the estimated values of the sigma with the original. It was 0.1, 0.08, 0.15, 0.2, 0.11. Those were the original values. These are fairly close to the standard deviation of the error. You can look at the eigenvalues after convergence. They have a very nice pattern, and you can show this again theoretically. All the eigenvalues corresponding to the number of equations in your problem will be 1, will be precisely 1. There is no heuristic here. You can show theoretically, if you have scaled your data correctly, the eigenvalues that you should get corresponding to the number of constraints should be precisely equal to 1. All of them should be equal to 1, and that turns out. Remember, in this case I don't know sigma, I am estimating it from data, but nevertheless you satisfy the condition. So you can pinpoint, if you guess the number of constraints incorrectly, this will get completely distorted. You won't get this. So it's a very good check, cross check, of whether you have guessed the number of equations in your problem correctly. That also can be found out. So what we are saying is that you have actually solved all the problems. Given data, you can find the number of constraints, find the constraint matrix or the row space, a basis for that. You can find the sigma, the error associated or inaccuracy in the data, and so on and so forth. All of this is possible. And although I have shown a small example, you can take a 1000 variable case and you can still do it. And we have tested this on extremely large examples, and it bears out. Okay, so it's not as if it's only applicable for small scale problems, because PCA is a very nice algorithm. It's a one shot. There's no iteration involved in finding the eigenvectors, right? It's just when I say this, although it's not an analytical result, but still numerically it's a very SVD is a very stable algorithm. So you get the thing for large samples also you can do. Okay, so I've just basically I just want to stop there. I want to do a extension of this. How much time do I have? Okay, so I'll take about 10 minutes to show application in blind source separation. And here it's actually a chemometric example. This is a laboratory data set which borrowed from Wenzel in Canada. So they have taken mixtures of cobalt, chromium and nickel salts in nitric acid, and they prepared a 3 factorial design. So 27 mixtures they prepared at high, low, medium concentrations of these, but still well within the fairly dilute so that you can apply Beer-Lambert's law. So the mixtures were prepared, 27 out of which 1 was thrown out, and then the UV spectra of these mixtures was taken, and this was replicated 5 times for a certain reason. So you have 5 replicates of 26 different mixtures measured at 176 wavelengths between 300 and 650 at 2 nanometer intervals. The absorbance was taken. So essentially you have 176 data points corresponding to each mixture of 130 samples, but these 130 samples actually represents 5 replicates of 26 mixtures. So typically you have 26 mixtures by 176 wavelength as your data matrix, but there is a replication of each of the rows 5 times. Okay. So here the main aim is to take this mixture spectra and find out, remember, although there is 27 mixtures of 176 wavelengths, actually it is a weighted combination of only 3 pure species which corresponds to the cobalt, chromium and nickel salts. So essentially you have 20 here 27 by 3 into 3 by 176. So this is a mixing matrix which represents the concentration of the different salts, and this represents the pure component spectra. What you want to do given this is to get this, and also find, if you possible, how many pure species are there. Typically you don't know the number of pure species, you don't know the mixing matrix, you don't know the pure component spectra. Remember, PCA does somewhat there close, but it finds a basis, it doesn't find the pure spectra. It goes up to a basis and stops there. So you need to put in additional conditions in order to get to a particular basis form. Okay, otherwise I would have taken this B to be U1 and S to be the remaining. Notice that, you know, if I do an SVD of Z, I could actually consider U1 to be B, S1 V1 transpose, which is smaller dimension, okay, because you have retained only a few principal components. So this particular thing could be considered as a source spectra, and this could be considered as the mixing matrix. It's a particularly, I mean, it's a solution. PCA will say take it, I found out, but this is non-unique. Any rotation, you can actually rotate it and get a different solution. So it's only a basis for that pure component space. So this represents some linear combination of the pure species spectra. It is not the pure species spectra. So you are looking for a particular rotation. Another way of interpreting this problem is, you don't know this rotation matrix, you can multiply U1 multiplied by M inverse this. What is that M that gives you the pure component? What additional conditions you need to stipulate for getting the pure component spectra? What are the conditions? So that you get all the elements of M, the rotation matrix. So different people have come up with different techniques and have called it by different names. So if you go back and look at the biology fellows, they have put structural constraints. They said certain elements of M are zeros, and I will actually solve for the remaining non-zero elements. That way they resolve the rotation matrix problem. NMF, the chemometricians have actually said, okay, let me put non-negativity constraints. After all, I know that the concentration should be positive, absorbance should be positive, mixing, okay, pure component spectra absorbance should be positive. Why don't I put a non-negativity constraint and hope for the best? Okay, it doesn't resolve the problem, but hopefully you will get the proper basis. Okay, so non-negative matrix. So they developed non-negative matrix factorization. In image analysis also this is used. A third person said, okay, fine, let me actually assume they are non-Gaussian. Okay, the spectra is not a Gaussian signal, so let me use some non-Gaussian, and if you mix non-Gaussian, central limit theorem says that you will come to close to Gaussian. So when deconvoluting, I will ask for those spectra which are as non-Gaussian as possible. Use Kurtosis or some other measure of non-Gaussianity, that comes out to be independent component analysis. So different people have looked at this problem, put additional conditions in order to sort out this problem of rotational ambiguity. So here I am just going to talk about the simplest, which is non-negativity, which we can verify. Everything else is unverifiable. This assumption we can actually verify in at least in chemistry, chemometrics. Basically it says, let me impose the additional condition that Bij, elements of Bij, which is the concentration, should be non-zero, which we know to be true. Elements of S, which represents absorbance of the pure species, should be non-zero, which is also known to be true. So we are not putting conditions which are unverifiable. We are making assumptions variable and then do it, and that particular procedure is called non-negative matrix factorization. So you are factorizing this matrix Z into two matrices of smaller dimensions, smaller number of columns, such that the elements of both these matrices are non-zero or positive. Okay. So okay, this is just an experimental data set, 5 mixtures, showing you the spectra spread over the thing between 350 and so on, and also the error variances. So you can also compute the error variance. Actually it turns out that it has a boat shaped curve, 350 to 600 is more or less flat. The variance actually starts increasing at the ends of the spectrophotometer, which is typical behavior of an instrument. Ends of the instrument, its inaccuracy is more. Middle of the instrument, they actually say it's fairly accurate. Even the instrumentation manual will say this. So when selecting an instrument, typical recommendation is your operating point should fall close to the middle of the instrument. Then you're likely to get more accurate what you call estimates from the thing. Okay. So the optimization problem I have just stated, you are trying to estimate Z such that Z is given by this combination where B and S should be positive, but the B is a smaller dimension. Okay, S is less than N. S is number, N is the number of variables, S is number of sources. Here you are looking at the retained, not the rejected, not the complementary, which I was doing in the linear model case. Again, it turns out NMF was developed for the deterministic case without worrying about the noise assumption, but typically you can show that the way it's set up, it assumes that errors in all variable samples have all identical variance, and errors are mutually independent. Otherwise, you can't show that this function has a likelihood, it's not a likelihood estimate. So it basically makes the same assumption about the noise as PCA has done and solves the problem. I've just applied NMF. This time I've done a PCA based pre-processing to the data, so that I've reduced the dimension to the required number, which is 3. In this case, we know it is 3. We have not looked at eigenvalues, nothing. I've just assumed that I know the number of species, done a reduction, and then extracted the sources such that this is non-negative and so on, did the rotation, if you want to call it that. And this is the true spectra, the dotted line, measured using the spectrophotometer for each of these pure species. That data was also available. This is the extracted spectra from the technique, NMF. Notice that these two are done fairly well, but this one has some what I call mixing with this. This is not completely demixed. So cobalt is most difficult to estimate. Nickel and chromium, pretty much different techniques seem to do a reasonable job. This is a little further away, this is almost there, this is far off. Notice that the error variances were different. If you do the pre-processing using IPCA, which we have developed, and a little more variant of this, which uses the functional form, you really get very good estimates of the thing. So this is again just to show how you can actually, with no replicates, nothing. All of this is done with just the 26 samples without using replicates. If you use replicate information, you can get a sigma value and you can scale it and do a good job. But this is done without using replicates. So you are estimating sigma, estimating the sources, estimating the mixing matrix, everything from data, just from data alone. So this just shows you the kind of correlations that you can get between the measured true spectra and the estimated spectra. So this is a source separation problem, and this is a very small variant of what we did from the IPCA. This uses what I call denoising in both ways. Typical denoising techniques in electrical engineering use univariate techniques. They use a Fourier series, for example, and cut the high frequency out, or they use a wavelet based denoising technique. All of that are univariate. PCA uses what we call multivariate because it uses interrelationship between different signals for denoising, right? So you combine the two what I call two ideas together, and the functional PCA does that. And you can actually make a variant by using IPCA, where estimate of the variance is done from the data and scaled properly. You can really get a very good separation, source separation. So this is just to show you. So what are the basically I've only shown 2 examples, but it turns out mixing models are present everywhere, all over the place. There are lots of techniques which uses linear mixing models. So the first thing that we are asking now is, can you do model? What we are most interested in is model development. So what if some of the constraints in the process are known? So like I said, I know the partial network, water network, or a partial connectivity network for a power distribution, and I know energy flow meters are there, okay, which is the conservation, which basically should obey the conservation law. Is it possible to figure out what part of the network is missing, and is it possible to construct the entire network from data? It turns out that it is possible under some condition. So knowing some of the constraints, or knowing the structure of the constraints, or can I construct data? These are interesting questions that you can ask, which have some practical what you call utility also. So this is the direction in which we are actually making some what I call modification to the method. We are also doing the same thing analogously. Can we do this for nonlinear models? Static first, and then to linear dynamic models. So those are 2 directions in which we are moving as far as these extensions of these methods are concerned. So I just acknowledge several of my colleagues from Alberta, and also other students who have done their masters and PhD with me, and currently many of them I've converted them into doing a PhD so that they can also propagate the same. May the tribe increase the tribe, what they say. Okay. So questions in just
PCA method. I mean, so is there some equivalent of like what's it called, successive, or like, you know, what's it? I forget. I mean, I'm trying to take an analogy with.
Okay. I can show. There are certain things. Whenever you have these product terms appearing in your objective function.
Right.
For many things where something can be here, you can see that the estimate that you are going to derive is a product of 2 quantities.
Right.
A matrix, you can write it. So you can keep one matrix fixed and solve for the other, and keep the other matrix fixed and solve for this. Those are called alternate least squares methods.
Okay.
Right. So this is not an alternate least squares method.
Okay.
Alternate least squares methods have very slow convergence properties. They are not known to. This actually uses some. It knows that if you, in this case, one of the solutions known. If I give you a sigma, I know the solution. Analytic, I know the solution for it. So why to solve this iteratively? So basically, that it exploits PCA's already prior knowledge in the iteration. So it converges very fast. That's one of the advantages. But you could do alternate least squares kind of techniques also.
Any other question?
Constraints and variables.
Yeah, for the let me put it this way. There are 2 stages. One, if you know the error variances, then the proof is straightforward thing. What you call derivable. That's unique. You will get it. In the case of when you are trying to estimate it from data, if the identifiability condition is satisfied, then you will get a unique solution. That's also known. The identifiability condition is how many elements of sigma can you estimate really. And that's well known in statistics. It's written in the linear regression thing. Under a certain framework, this condition has been established, and we can derive the same condition here. So if you are not that is, you can't try to estimate the entire sigma. The full sigma is never possible. That we can show. You can estimate a part of it. In the case of diagonal, typically most problems you can estimate, because there are enough constraints for you to what you call estimate uniquely. Now, whether the algorithm will estimate an accurate sigma is a different question. Can you show consistency of the estimates? We have never been able to show consistency. That is, in the limit of large samples, will the estimate converge to a truth? That question we have never been able to prove analytically. So I've been looking for a mathematician who can look at this and do something, help us out. But convergence of the algorithm we are able to prove. That's where we are stopped. That algorithm converges, there is a unique solution we are able to show. But whether this will give me the consistent estimate, we have not been able to show. That's where we kind of know there's a gap.
So as you gather more and more data, you're not sure.
Yes, but what I call numerical results seems to show it. I'm not able to prove it. That's all I can say. But numerical results seem to show it converges. But that's you can get fooled by it.
What are the dependent variables or independent variables?
Yeah.
So if we give a set of data and then do PCA,
okay,
Is there a measure which will tell us that?
Yeah, I just show you one step, and it's very clear from the way it's written. This step basically shows you how it's, what you want when you take independent variables, set of defined from the set of variables. After you have found out the implicit form of A, you want to convert it into this form. For converting it, you need to be able to invert AD. So if you have selected the correct set of independent variables, then AD, the condition number of AD will be very good, will be small. Whereas if you have given me incorrect, the condition number of AD will be large. So you can write the condition number for every combination. After you have estimated A, arrange them, and you can actually show there is a clear break between those that you can consider as independent, those you cannot. There are different combinations you can have as independent. It is not that there is a unique combination. There are different. And all those combinations can be found out by just checking the condition number of the corresponding AD submatrix of A. So you can have a formal test for this, numerical test, which will tell you from given data how many independent variables are there by looking at the eigenvalues, which set that you can actually define as independent variables by looking at the submatrix here and looking at the condition number.
So, but you have to choose randomly some of them and then.
Not random, do everything combinatorially.
Yeah, okay. I mean, if not
do everything.
But
every subset you choose, look at the condition number and order them from highest to lowest, and there will be a clear indication there.
Keep checking until you find the.
It will tell you all the possibilities. You ask me one set, I will give you all the possible sets. That's what I am saying.